I think getting into science was not what I had originally wanted to do. I started off as an engineer at the University of Wisconsin, and I was somewhat more free thinking than the engineering school, at least at that time, was allowed me to do. So I quit chemical engineering and went into biochemistry, and got really engaged in, originally as a volunteer in the lab of Professor Roland Rickert. And since then, never looked back, because I was always fascinated by what we could see in a test tube every day, and it's different. After my really very educational training with Roland Rickert, Wisconsin, I joined the laboratory of McCullough, Ernest McCullough, who discovered hematopoietic stem cells in Toronto. And I learned a lot from him, in the sense that he's a very free-thinking person. And then after that, I went back to the University of Wisconsin and joined the laboratories Howard Tammon, where I learned a fair amount of retroviruses. And there I learned how to do subtraction hybridization to isolate genes that cause cancer by retroviruses. And ultimately, that helped me, and incidentally, Mark Davis, in a completely independent way, to be able to clone the T-cell receptor, because the subtraction hybridization was the key to cloning the T-cell receptor at that time, before there was enough technology to be able to clone the T-cell receptor in any other way, at least at that time, including proteomics, which was what most people wanted to do. So I think along the way, I was lucky, not only in the sense that I kind of learned a lot of thinking, free thinking in a way. Roland Rickert was very, very regimented. He was American-born, but German background, and still very regimented in thinking. McCullough was more of a poet, and he was able to think kind of out of the box. And then finishing off with Howard Tammon, who not only was a brilliant thinker, but also was very insightful in the approach or the approaches that need to be to solve a problem, and always ask why. So I think I owe my whatever I have achieved to these mentors, and of course to the 150 trainees. Well, I wouldn't call them trainees, because actually I trained with them, because I learned more from them over the last 40 years now. So that, in summation, is what I think the end result of three brilliant, insightful, just kind and helpful mentors, and then over 100 trainees over the years, that somehow ended up with what we could achieve during the last 40 years, of which I am extremely grateful. Well, I think after 40 years, I've earned at least the opportunity to say a few words about the mentees. I think it boils down to 3 words in a very, very simple way. There is an author by the name of Simon Sinek, who wrote a book, and the title of the book is Always Start with Why. And in a nutshell, what he is saying is that a lot of organizations know what to do. Some know how to do, and very few ask why they're doing it. And I think as a scientist, especially in this very mature field compared to when I started, we were still using sucrose gradients. We were still doing Southern blots. Those things don't happen anymore. And so what you think is what you can do and how you can do it no longer is competitive in the sense that you could actually contribute to the future. So I would, as Simon Sinek said, always start with why, because those why questions are going to help you compile a network of theories and thinking and hypotheses that in the right setting with some luck, you could actually come up with something that no one have either thought of or have done it in the way you did it, and allow you to come up with a new conclusion. I should add, in this kind of era where a lot of machine learning, robotics, bioinformatics, artificial intelligence, all those are extremely important in filtering data. But I caution the young people to think that is in itself the end of the whole pursuit. I want to quote Richard Feynman in saying that if you are going nowhere with a slow technology, developing a fast technology only gets you nowhere faster. So it is very important that machines, learning, bioinformatics, high throughput screens, all these are important, but you really should learn how to think about the biological problems before you even apply those technologies, because those technologies are only there as filters for data that you could actually spend more time thinking. And so please don't always just take what the bioinformatics people tell you, the top 10 candidates and the bottom 10 candidates, and consider that is the answer to all questions. So in other words, please go back to thinking about the biological problems in addition to having machine learnings and bioinformatics and high throughput screenings, etc., helping you filter the millions and millions of data points. I am, first of all, flabbergasted for someone who never considers himself being, well, worthy, maybe not the word, have contributed enough to be recognized in this very profound manner. But at the same time, I should humbly accept it and thank all the trainees and my mentors who, over the last 40 years, helped me not only to think about the problems that are important in science, and in this case, immunology, but also to apply them and to help patients who are without any other possibilities to relieve their syndromes and their sufferings. So I hope that this will also encourage myself and my group to further our investigations and explorations into the field of immunology applied, in this case, to cancer. There are still lots and lots of questions that we can ask, and lots of new theories that we have yet to uncover. We are nowhere near understanding immunology the way we think it. When I started in the field of immunology, I was told that everything is solved. In fact, the more I have been involved in the last 30 some odd years, the less I think I know. Just for example, very recently, with the collaboration of Kevin Tracy at the Feinstein Institute, our laboratory has embarked on a new path to study immunology in the sense that the brain actually talks to the immunological networks. What we, in a nutshell, discovered was that lymphocytes can make the neurotransmitter acetylcholine. And we published, we means a very talented postdoctoral fellow who is now a professor at University of Oklahoma by the name Maureen Cox, definitively prove that acetylcholine is necessary, made by immune cells, in this case T cells, and that if the T cells cannot make acetylcholine, which is crazy in the way that we are thinking, because no one would expect immune cells to be able to make acetylcholine, let alone that the production of acetylcholine by immune cells are absolutely necessary to clear a chronic virus infection. I don't want to belabor the point. This is just one of many aspects of immunology and wrinkles, if you wish, or another lens to look at the problem. There are many more of these out there that will help us to further understand this very complex network, which today, through the work of many people, including Jim Allison and Tasco Honjo and others, we have reached the point where immunology as a tool to treat cancer is now the fourth pillar for cancer treatment after surgery, radiation, and drugs. So please do not think that there are no paths ahead. There are many new paths. We just have to be patient. We have to be lucky. But most of all, we have to be determined and to always ask why.